Yeah. OK, so I guess my interests are in, well, derived categories of coherent sheaves and algebraic stacks and all that kind of stuff. But I mostly come to it from the perspective of, my interest in algebraic stacks comes from the idea of unifying ideas in representation theory with ideas in kind of geometry and moduli theory. So hopefully, we can start with a nice down-to-earth example. So this is kind of a strange formula, this thing right here, when you look at it. It's some kind of, so I define some polynomials and consider the Poincare polynomial of various topological spaces, and I identify a relationship between them. And it's, it might be kind of inert, it might be kind of interesting to you. It could, if we didn't already know what the cohomology of the Grassmannian looked like, it might even let you compute that cohomology. But of course, well, I guess in more complicated examples, you can actually use this for that effect. The reason I'm interested in it because there's a very rich geometric story behind governing this formula. So when you think about it, the way that you construct the Grassmannian is by starting with this very simple vector space with an action of GLK. And you identify the Grassmannian as an open subset of that vector space, the so-called semi-stable locus, modulo the action of this group. But in fact, so if you look at what this formula is saying, it's saying that there's some kind of invariant of the semi-stable locus, which is the Poincare series of the Grassmannian. And then the correction terms come from other strata in the original vector space that you started with. So in this vector space, you can look at Z naught would be the semi-stable locus, those matrices of full rank. And then you can look at also the matrices of rank 1, the matrices of rank 2, all the way up to full rank. And what this formula about Poincare polynomials really comes from is some kind of other expression, one category level up, about cohomology groups. So what it's saying is that if you consider the so-called the cohomology of the stack, well, this vector space modulo the group, that should be just the equivariant cohomology. Well, I mean, this vector space is kind of equivariantly contractible down to the point. So you can think of this equivariant cohomology as just the cohomology of what you might call the classifying stack, which is exactly what that formal power series is the Poincare polynomial of. So this is saying that you have a vector space decomposition of this equivariant cohomology group here of the ambient thing, which in this case is very easy to understand. And it decomposes a direct sum of the equivariant cohomology of the thing you might be interested in, the semi-stable locus. And then there are other contributions coming from these other strata. So these are contributions coming from the lower rank matrices, the locus of lower rank matrices. So I guess that's the starting point. And that's what I'd like to kind of generalize. So this direct sum decomposition on cohomology is expressing something very special about the stratification. So you can always, if you consider kind of cohomology groups, you can always restrict. You can consider it like a smooth subvariety and restrict to the complement of a stratum. And you always get a sequence of cohomology groups like this. But in fact, what this formula is expressing is that in this case, this sequence is short exact. So it's something special about the stratification that gives you that this direct sum decomposition. And the other reason why kind of this has been intensely studied is because it comes from an analogous story on the symplectic side, which is that you can think of this vector space, in this case V, has a symplectic form on it. And when you have a symplectic form with the action of a compact group, in this case the unitary k by k matrices, you can kind of construct the so-called moment map, which in this case just takes the k by n matrix and whoops. So the moment map is always just a map, a k equivariant map from your symplectic manifold to the dual of the Lie algebra of the compact form of the group that's acting. So in this case, it's a map with values, a map on V with values in skew Hermitian matrices, like this. And there's actually there's a natural norm on the space of skew Hermitian matrices, which is this trace of the matrix times its adjoint. And this stratification actually has interpretation in differential geometry as the Morse stratification for the gradient descent of this norm squared of the moment map. And so you can actually phrase this and think about this for arbitrary kind of symplectic manifolds with Hamiltonian group actions. It doesn't necessarily have to be connected to algebraic geometry, although I guess kind of what I come mostly from the perspective of algebraic geometry. So, in fact, this picture, I mean, I showed you for the Grassmannian, but you can do this for any time you have a smooth projective over affine variety. You get a stratification of this form, which you can either think of differential geometrically as a Morse stratification, or you can think of, there's a purely algebraic definition of it that works over other fields. And this kind of decomposition in cohomology, is always holds in that case. And in fact, there's lots of ways to extend this result. You might even say this is some kind of motivic decomposition of the quotient stack, that any kind of cohomology theory that you can cook up, it turns out that you get a direct sum decomposition like this. So people have done topological K theory and complex cobordism and things like that. And also it's kind of a direct sum decomposition of Hodge structures, if you can make sense of that, and things like that. So I guess the thing that brought me to this set of ideas was that I noticed that there was a purely algebraic version of this story, which is that you can consider to any variety or stack or anything like that, you can associate this object, which is a category. It's called the derived category. So concretely, you can just think of it as taking the thing you're interested in and considering studying the category of all complexes of sheaves on that thing up to some notion of equivalence. And in fact, what you get from this stratification is something like a direct sum decomposition of the equivariant derived category that mimics the direct sum decomposition in cohomology. So I mean, the actual thing is called the actual technical thing is called a semi-orthogonal decomposition, but effectively it kind of looks like a direct sum decomposition. So in particular, the derived category is kind of like from the algebraic perspective, that's kind of like the Uber theory of all these different cohomology theories, because you can recover algebraic K theory from the derived category. You can actually recover kind of equivariant cohomology in like the topological sense from the derived category. So this is kind of like this is one category level higher than the direct sum decomposition on cohomology. This is showing you kind of the structure that's underlying that in a certain sense. Yeah. So right. So in our case, this gives you, well, yeah. So I mean, the derived category version has other kind of features that are nice. So it's more than just it gives you more than just direct sum decomposition of the various kind of topological invariants you might try to extract from the derived category. It gives you well, you can compute the so-called K-theoretic index. So you might be interested in computing the G invariant part of some sheaf cohomology groups. This Euler character, this thing here is kind of, it's also related to some index of some operators via an index theorem. So this is the kind of a natural thing to study from the perspective of K theory. And it also has a shadow in cohomology. But the point is that this expression, you can actually just think of this. This expression turns out is like the virtual dimension of the space of maps between two objects in the derived category. So you can actually realize this kind of numerical thing, which is like the virtual space of global sections of some object in the derived category, some vector bundle, some equivariant vector bundle. This gives you a way of expressing it. What you end up with is saying that the kind of the virtual global sections of the vector bundle on the entire stack, well, you get the virtual global sections of the vector bundle on the semi-stable locus, and then you get some correction terms, which I'm not going to really describe the detailed structure of, but you get some correction terms, which are the virtual global sections of that vector bundle restricted to each of these special strata. So that's a
formula that holds for any algebraic group acting on an algebraic variety.
Well, so there's some, so, oops, yeah, so.
Do you suppose there are only finite Riemannian strings?
Yes, but I mean, if you're in the finite type situation, then that's kind of okay. Yeah, and so. I mean, this is the decategorification, so to speak, of a local cohomology sequence, which works if you have any subvariety of any variety, you can kind of, you can kind of decompose as a long exact sequence the global sections of the restriction of the complement, the global sections in the whole thing, and then some other piece. The magical thing in this case that makes this formula have content is that if this thing has finite dimensional cohomology groups, then this will also have finite dimensional cohomology groups, and this will also have finite dimensional cohomology groups. So that's not something that typically, that's a very rare thing to happen. Like it's saying, that if you take an open, in fact, it never happens for just a scheme. If you take an open subscheme and you take the derived global sections of if you take the sheaf cohomology of the restriction of a sheaf to that thing, it'll always have kind of infinite dimensional higher cohomology. So this is kind of another, that's the special fact that's underlying this expression. Oh, because this is only well defined if the groups are finite dimensional. Yeah. So I mean, this is useful. This kind of formula is useful if you, let's say you're in a situation where you already know this, then it's useful. I mean, typically mathematicians are kind of interested in the semi-stable locus because that might be, I mean, the original goal of thinking about the moduli problems in this way was that you started with a moduli problem. Maybe it was huge, like it may not even be kind of finite type. And so the idea is to systematically throw away bad points until what you're left with is actually kind of a scheme or something like that. I mean, that's what happened in the Grassmannian example. My perspective, I'm actually, I think the actual structure of the stratification itself is like a rich and interesting thing. And so I'm not exactly, necessarily just interested in the semi-stable locus, but no matter, you can read this formula in any number of ways. You can read this as a way of telling you what the global sections are on the stack, or you can read this as a way of, if you already knew what the global sections on the stack was, you could use this as a way to compute what the global sections on the semi-stable locus are. And there's even another way to do it, which is like very clever, which is that you could find another stratification of the stack that looks the same way, but one where the semi-stable locus is empty. And the left-hand side doesn't depend on the stratification, but the right-hand side does. So if you can magically find another stratification where the semi-stable locus is empty, then you get an expression for you can isolate an expression for the original semi-stable locus just in terms of these integrals on lower dimensional varieties. So.
I'm confused with the formula. Will V descend to something on the semi-stable modulo V?
Yeah, because everything here is a stack. So this is just an open.
So this is
it's just an open.
This is also an equivariant cohomology.
And it's also equivariant cohomology. Yeah. Okay. So I guess that's kind of that's all well and good, but I kind of noticed that there are hints that there's something more to this story. So there are kind of two reasons that might make you think that there's more than just Morse theory and Hamiltonian group actions and GIT in the world, and that is that. So it's actually chronologically kind of reversed here. That Atiyah and Bott kind of discovered this phenomenon before it was worked out in the finite dimensional case, and they discovered it on the moduli of vector bundles over a curve. And that's one of these cases where if you have like a Riemann surface, there's a notion of a holomorphic vector bundle, and you can say what you mean to have a moduli, the moduli problem of holomorphic vector bundles. Turns out that there are just too many holomorphic vector bundles. It can't possibly be parameterized by a single scheme. But if you kind of throw away bad points, you get to something that actually is a scheme. And and in fact, the moduli of vector bundles has, like the entire moduli stack of vector bundles has one of these stratifications where each of the strata has a nice modular interpretation. And this stratification, if you're familiar with it, is this stratification by the so-called Harder-Narasimhan type of an unstable bundle. So. I mean, there is a way. So the Atiyah and Bott contribution is by thinking of this as an infinite dimensional GIT, so to speak. You can think of this as it's a space of del bar operators on some fixed complex vector bundle on your Riemann surface, and then modulo some infinite dimensional gauge group. And you can actually squint and try to see this as a GIT problem. And in which case, this actually is still the gradient descent flow of the Yang-Mills functional. But that's hard to make sense of that in a purely rigorous way in algebraic geometry. I think, and for that matter, differential geometry. But anyway, the stratification you can just show has all of the same properties as the GIT stratification does. So it would be kind of desirable to have some intrinsic way of describing the stratification, because there are already examples popping up. This Halpern-Leistner filtration, this idea, comes up in other moduli problems where there's no global description, there's no kind of global quotient description in sight. You can talk about, Halpern-Leistner filtrations of coherent sheaves, et cetera. And there would be some nice way to just be able to describe this on the moduli problem itself, and with the eye towards discovering new examples of these stratifications. And the other thing is that there's a version of this theorem which still holds for singular stacks, even though the original thing you need smoothness. And there's a version of this theorem, and it's not really obvious how to get there. But if you reinterpret the stratification in a way that I'll explain, it turns out that you can put what's so-called a different derived structure on the stratification. You can kind of leave the world of normal algebraic geometry and put a different structure on the strata themselves. And with this new structure, the theorem just kind of works. It's kind of cool. So there's some underlying modular interpretation that you can give to the stratification, which is somehow more natural than just looking at it as a locally closed subvariety of the original X. And I don't know kind of what the status is. Probably this is kind of known already, but this, this would imply some kind of version of the Kirwan surjectivity holds for singular varieties with a different cohomology theory, some kind of equivariant Borel-Moore homology or something like that. Haven't exactly thought about how it boils down to something on a level of topological invariance yet. But so the modular interpretation that I'm going to give this thing is the following. So you can think about what is the modular interpretation of a point on the gradient descent flow of a Morse function. Well, you can think of this kind of naively as this represents, the disjoint union of the Morse strata for the gradient descent flow represents the moduli of points in your manifold along with the gradient flow line along with its endpoint, which lands on some point in the critical locus. So, if you consider that sort of moduli problem, the moduli problem of parameterizing actual flow lines, rather, gradient descent flow lines, then that's essentially the same thing as just picking one of the Morse strata, picking a point on one of the Morse strata. And you can frame this in terms of algebraic geometry. If you consider this stack C mod C star, and you consider a map to the moduli stack that you're interested in, that's essentially the same thing as having kind of a potential gradient flow line if there was a GIT story in the background. And it turns out that the actual gradient descent flow line is the map from C mod C star to X, which maximizes a certain numerical invariant that you can associate to such a thing. So anyway, you can give this strata a modular interpretation as the moduli of maps from C mod C star into your original moduli problem that satisfies some kind of numerical property. Yeah, and this is the modular interpretation that allows the machine to kind of churn in the case when you have a singular quotient stack. Oh, we're over? Oh, okay. Sorry. Well, this is it. That's fine then. Sorry about that.